In mechanical engineering, there are a lot of situations where we'd like to know the position or velocity or acceleration of an object, or all three, in order to know where it is, where it's going, and how quickly it's going to get there. So in this video, we're going to talk about techniques, a small selection of techniques we can use to measure position, and from that position measurement, derive the velocity and the acceleration. Because velocity is just the slope of the position with time. It's a derivative with time of the position measurement. And the acceleration is just a time derivative of velocity. So let's look at how we can get that data. The simplest way, and the one that you're going to see in the lab, is to use a potentiometer. And usually potentiometers are rotational. You've already used some. This arm turns in the middle here, and it moves along this variable resistor. So if we have a voltage source connected across the whole resistor, the two outside pins on a potentiometer typically, then we'll have a voltage on the output from the moving arm that varies ideally linearly with the position of the arm. So if we measure the voltage here, we should be able to figure out what the angle theta is around that rotational motion. And we're going to measure that kind of rotational motion in the lab. Now, some potentiometers go more than just 360 degrees around. A typical one you might find would be a precision potentiometer that would go 10 times around to change the resistance over a 10K band, so that it could go around and around and around and around. And traditionally, these potentiometers were made by winding fine wire onto a substrate, and then the contact would slide along there, making contact with only one of those wires at a time, so the total resistance would change with the length of the wire that was in the circuit. Now, the result when you do that is that it's going to go stepwise from one wire to another, and you'll get this stair-stepping effect. But in practice, current potentiometers are mostly made with carbon conductive elements here, and you're sliding along a continuous carbon pathway, so you're expecting a continuous straight line as a function of position rather than a stair-stepping like this. And if you take that potentiometer, put it in here, here's a high precision potentiometer, and add a tape like this, a precision steel tape with a recoil spring in there, then as I pull out this tape linearly in this direction to detect linear motion, it'll rotate this potentiometer, and I can use that to translate into a linear position based on the rotational position of the potentiometer. And these are quite commonly used devices for measuring linear position. For instance, as mechanical elements move back and forth along some known distance. Now, this has got the considerable advantage that if your extension is maybe up to a meter, you don't need a measurement device that's a meter long. You've got this tape that's pulling out and going back in. So, although we'll work in the lab just with a rotary potentiometer and measure rotary position, it's important to keep in mind that these things are commonly used to measure linear position, which is something that we're often interested in from a mechanical engineering standpoint. So the advantages of using a potentiometer for position measurement: it's really simple, it's linear, it's cheap. It's got a really easy to use analog interface and a large range, so that it's really easy to plug into a microcontroller or something like that. And it retains its position registration without power. If I move a potentiometer and then I turn off the power to my measurement system, and then I turn the power back on, I'll still have the same information about where the position of that potentiometer is. That's an advantage that isn't going to be really clear until a little later on, when we look at encoders, which don't necessarily retain the position without power being applied. So disadvantages, well, it's analog, so we need to calibrate it. It's got all of the noise issues associated with analog instrumentation, so we're going to have to accept a certain level of uncertainty in our measurement. Mechanical wear, these are mechanical pieces that rub on each other. So that limits the cycle life. They won't last forever, but they can be quite durable and last a long time. It's just a factor you need to work into your design to make sure that you're going to be able to manage enough cycles to make the measurement you need to measure. Limited range. For example, it will only go maybe 10 turns. It won't allow you to rotate it continuously and indefinitely. And of course, with the manufacturing tolerances, it will not be perfectly linear. It should be pretty close, and the more money you're ready to spend, the better that linearity will be. So potentiometers, really useful, practical devices for measuring position. If you need to measure position that's moving a little more often or moving a little faster, then you probably want a device that doesn't have that contact friction. And a linear variable differential transformer, or LVDT, is a device like that. And it takes advantage of the idea that if I have transformer coils and I run a constant AC voltage through this primary coil here, then these secondary coils will pick up an AC voltage that depends on the current that's flowing in the primary coil. And like most transformers, if you put an iron core into those coils, that directs the magnetic field lines much more effectively and couples the two coils together. So if I've got this core symmetrically placed in this transformer, then I'll see an equal voltage induced in each of these two secondary coils as a result of the AC voltage going through the primary coil. If I move the core, then I'll increase the linkage between the primary and this coil 1 secondary, if I move the core over here, and I'll decrease the magnetic linkage between this primary coil and coil number 2. Now, if these are wired in opposite directions, then I can get a measurement out here that's the difference voltage. So when the core is right in the middle, this difference voltage will be 0. When the core moves this way, this difference voltage will go in a positive direction. When it moves this way, it'll go in a negative direction. So as a result, we can get out a measurement here that should be directly related to this core position. And as this core moves back and forth in this cylinder, it can move continuously. It can be designed so it's low friction. It'll last as long or longer than any of the mechanical parts in the system. And it will give us a fairly fast measurement of this output so that the AC voltage coming out will give us an immediate indication of what the current position is. So that's what it looks like. And here's what the output will look like. As we move the core to one side and to the other, if we stay down here in relatively small motions of the core, we get a linear relationship here, so that the variation in position varies linearly. As we move further along, so that the core is moving further and further out this way, eventually we get a nonlinear linkage, and the result is we get this curve coming off here. And by the time we get over here, the core is right out of the sleeve. But as long as we stay in this region, we've got a good performance behavior based on the position and the core. Now, because this is an AC voltage, this difference voltage, we can't really tell whether it's positive or negative. That positive or negative sense shows up as a 180-degree phase shift in the oscillations of that AC voltage down here. So we're going to need something that allows us to detect whether we're in this side of the range or that side of the range. So we've got core motion that changes the AC coupling between the coils. It's linear over a small range as long as we stay in here. It's frictionless in that these don't need to actually be in contact, so there could be an air gap in there. And so we don't have any cycle limitations. And the range of position is really limited by the size of the device. So if I wanted to measure position over a distance of meters, that would be really difficult. I'd have to have a meters long linear variable differential transformer, and you won't really find those. So these are used for relatively small motions and detecting that position. And here's some practical drawings and photos of actual LVDTs. So relatively small scales, this might be 100 millimeters long. The advantages, very high accuracy if they're built to high tolerance, and virtually unlimited cycle capability. It does also, like the potentiometer, hold position registration without power being applied. So if I turn off the power and the core is in one position, I turn the power back on, the core is still in that position, and I've still got the information about knowing what position it's in. Disadvantages, I've still got to calibrate this thing, and the higher precision it is, the better my calibration is going to have to be to get the full advantage of that precision. I need to resolve the phase of the AC voltage that's coming out in order to figure out the direction, and I've got a limited range of position. So these will find some limited applications where you're trying to get really high accuracy position measurement. Digital encoding is what you'll get in just about all modern mechatronic equipment, where you're going to read the position by a series of digital pulses. So we're detecting position over time by the binary state of a sensor. So for example, it could be optically, either transmitting or blocking light if we are shining a light onto, for example, our photodetector. That was an example of potentially optical encoding. We can tell whether there's light passing or not. We could do it conductively by either connecting or not connecting a circuit. Now that would require some kind of mechanical contact usually, and that's a wear problem. Or we could do it magnetically by detecting the presence or absence of a magnetic field. Optically or magnetically are going to be the preferred approaches because we don't need any physical contact, so we can make these devices really fast and really low wear so that we can have a whole lot of cycles in our measurements. Now, if we do this digital encoding, then it's going to be largely independent of noise, and it'll be easy to follow with our microcontroller because all we're trying to detect is the difference between, say, 0 volts and 5 volts. We're not trying to detect an analog voltage. In addition, because it's just switching on and off, we can use the interrupt-driven capabilities on most microcontrollers to say, whenever it transitions from on to off or off to on, generate an interrupt, and we'll run some code to keep track of what's happening with the encoder. So these work beautifully for not having to be constantly monitoring them because we can follow them with interrupts. And here's an example of digital encoding. This motorcycle wheel, this brake disc, has magnets embedded in the brake disc around the circumference of the disc, and it's got this Hall effect sensor right here, which is detecting the passage of the magnets. So if we look at the signal that we'll get over time with our Hall effect sensor, and we just monitor it continuously, if it's going slowly, we'll see only a limited number of pulses. We're seeing 1 pulse each time a magnet goes by. If it's going faster, we'll see more pulses, and faster still, we'll see even more pulses. Now, the limits on this, of course, are in terms of the resolution. We can only detect when a magnet goes by. So we really don't know what kind of motion is happening in between. But we can use this to very quickly pick out velocity information by detecting how many passages it's gone, how many position changes there have been over how much time. And that'll give us a velocity indication. And this is commonly used for tachometer type applications, for example, to detect the rotation rate of something, usually in rotations per minute. And the circuit is really simple. Apply some battery power to a Hall effect sensor, and in this particular case, this U58-316, you put the positive on pin 1, you put ground on pin 2, and pin 3 will give you a voltage that varies depending on what the magnetic field state is in the neighborhood of this little Hall effect sensor. So this pin that goes to the Arduino, when there's the south pole of a magnet, the pin goes down to 0 volts. And when there's not, it'll be up at 5 volts or 3.5 volts or whatever the supply voltage is, pulled up by this 10 kilo ohm resistor. So here's another instance where we're using 10 kilo ohm resistors. 10K resistors, really common in all sorts of applications to either pull signals up or pull them down or provide a little bit of a load so that some current will flow. So these brown, black, orange resistors, you'll use quite a few of them. So that's how you'd set up a Hall effect sensor measurement, and you can encode the rotation of wheels or any other device that's rotating. Now, here's another example of encoding. This is an absolute rotary encoder, and this is only a 3-bit encoder. So we've got 3 bits of information here, 1, 2, 3. So in this one, it's 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. So if we think in binary, that's 0, that's 1, this is 2, that's 3, 4, 5, 6, 7. So we've got binary numbers encoded onto this, this sort of pie chart in a way that allows us to read from 0 up to 7 as we go around. Now, if I use some kind of optical device or magnetic device or any variation on that with this concept, I can divide this circle into 8 different octants. So I can detect 1/8 of a turn, and I detect it absolutely because I'll always get registration. If I'm in this position, it will always read 7, even if I've turned the power off and turned it back on again. So this 3-bit sample is an example only. You wouldn't use a 3-bit version because you'd probably want to detect more than 1/8 of a turn. But it's not uncommon to have encoders that go up to 16 bits. So that would split the circle up into little tiny segments. 16 bits is going to be about 65,000 of them. So that's 5/1000ths of a degree. So very precise rotational position. Those are expensive, but you can go 10 or 12 bits with much more affordable prices, around $40 a unit for rotational encoders. So 12 bits, that would be 4,096 different segments around the circle. That's also a really high resolution. And this little exploded view down here shows an example of an actual either 10 or 12-bit angular encoder that is magnetically based. So it's getting information out of magnetic variations as you rotate the encoder. So that'll give you an absolute size. $40 a unit, that's a little bit more expensive than our potentiometer. However, it has the advantage that because it's magnetic, it's virtually unlimited in terms of cycle time. Then, if the opposite of the counterpart of an absolute encoder is an incremental rotary encoder. And what this does is it'll have 2 tracks, just 2 channels on the disk that interrupt, that go from 0 to 1 to 0 to 1 to 0 to 1 on the 2 different channels. So if I have my disk and I have a whole lot of on-offs around the disk, then I can detect how quickly it switches on and off, and each on-off switching will correspond to a given amount of motion. This has the advantage that I can encode much more, many more changes in one rotation of the disk. The disadvantage is that I don't get the absolute position information. I only get incremental information. So I know if I start here and three tracks went by, three cycles went by, then I had moved this far on the disk. And I can know if I've got two different channels, which direction I was moving based on which of these two signals is leading or lagging the other. So these two channels are 90 degrees out of phase with each other. So that means they're in quadrature. And depending on which signal is leading in time, that will tell you whether the channels on the disk are moving in this direction or moving in that direction. And if we wanted to actually get some absolute information, it's quite common to also have a third track on there that just has one blip on it so that we can detect our registration after power loss. So after we've gone through one full rotation, we can figure out where we are in the rotational scale and follow along from there. So these incremental rotary encoders are very common in all sorts of applications, and they also have the same advantages that went with the absolute encoding and the Hall effect sensor, in that they can be incorporated into a microcontroller system really easily. Because what we're looking at here, just digital pulses that are switching on and off. We can detect those on interrupts, and we can monitor to see how many pulses have gone by. So really useful technique to get your data out. Now, mechanical encoders incorporate the same kinds of ideas for incremental encoders. However, they won't last as long as either optical or magnetic encoders, because there's actual switch contacts in there making contact to detect how far things have rotated. Now, mechanical encoders like this, the place where you would find one of those typically is on the front panel of your car stereo. So if you got into a really old car and turned on the radio and turned up the volume, and then turned off the car and turned down the volume, when you turned on the car again, it would come on at a lower volume because it was using a potentiometer to actually change what's going on in the circuitry. But in a modern car stereo, if you turn down the volume knob after the ignition key is turned off, it has no effect on what the volume will be next time you turn on the car. That's because this encoder only provides information to tell the stereo what to do when everything's turned on. So the motion is only providing little ticks that say turn down the volume a little bit. It's not actually changing the circuit characteristics to change the volume. So these mechanical encoders are good for lots of practical problems where you're not going to be having either a long life or many rotations. So these mechanical encoders, they'll last the life of a device if you're using them as manual controls. They won't last the life of a device if they're rotating continuously for the working life of the device, unless that working life is expected to be really short. So these are a bunch of ways that we could have found out position. To find velocity, we usually calculate that from some delta x, some change in position, over some delta t, some change in time. And that numerical differentiation really depends on the accuracy of both delta x and delta t. So as an example, you might measure the RPM of an engine or something like that by detecting a pulse from a Hall sensor every time the engine went around. And then if you count the number of pulses over the course of 1 second, so that would be the number of revolutions that you got in a second, then you would be able to calculate the revolutions per minute by multiplying that by 60. So this counting approach here, counting over the time of a second, gives you discrete steps of 60 RPM because you're going to multiply the number of counts that you got by 60. So that's a fairly rough measurement if you've only got one count per revolution. But the more counts you have per revolution, the better your RPM measurement is going to be. If we had a 60-line incremental encoder, that would give me 60 pulses for each revolution, and that would get me a 1 RPM resolution on the average speed at which my engine was rotating over the course of a second. Doesn't give me so much in the way of instantaneous speed, though. For that, I would need to detect the time between two pulses and then do the calculation from there. But the idea is the same throughout most of our velocity measurements, whether they're rotational velocity or linear velocity, usually calculating from a change in position divided by a change in time. Problem with that is if it's analog data, we've very often got noisy position data. So if this is position and this is time, then if we're trying to take delta x over delta t, and we take it between, say, that point and that point, or this point and this point, we might get a slope like this red line that isn't representative of what's actually going on in some average sense. We're getting a derivative there that's really a derivative of the noise. It could get even worse if the noise is going down this way between these 2 points. I could get a line that was not only the wrong magnitude, but totally the wrong direction. So calculating this as delta x over delta t, we've got to make sure that both delta x and delta t are long enough and large enough that we're getting a derivative that's close to the slope of the signal and not the slope of the noise. And this is something that we're gonna run into in the labs when we're trying to make some measurements with potentiometers, and you'll get some practical experience in figuring out just what should be the time that we take in order to get some practical estimates that don't have too much noise in the result that we're estimating for that derivative. So when we go to differentiate a signal that's got some analog noise in it, we really need to do some smoothing on the data. If I take that signal, which has got a fair bit of analog noise in it, and smooth it to something like this, numerically it looks pretty smooth. But if I take a derivative of that by sampling at different positions along the way, I can get answers that are just plain noise. This is really not the information that we were looking for. So that's a practical problem in doing that differentiation. And we're going to tackle that in the lab session in this week's active learning session. So keep in mind that when you're trying to measure velocity or maybe even acceleration, you're having to differentiate, and you have to be very careful to avoid getting a derivative of the noise instead of a derivative of the actual position and motion.